Hello, 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 hello. It is I, Ralph Yutz, your Stats 2 instructor. Here we are. Hello, hello, welcome, 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 welcome. It is a quiet final day here in the world at Sylvania. Good morning, good morning. A nice chat to good morning. All right, so far there are two of us. Let us see how many folks arrive interested in questions before our final next week. I've got a few ideas of things to discuss, though I'd be more interested in your ideas if you've got any on your mind. Dump them in the chat and we will discuss them. And let's give it a minute while people, anyone else making it through the mist out here in Southwest Portland or making it through their, devices, various distractions slash things that aren't distractions, things that require people's attention that they just need to deal with. Yeah, and then we'll get into it. Some statistical stuff. Hmm. Um, while we're waiting for folks, let's just double check and peek. I know that some people who don't make it to class do check out our YouTubes. So let's right here at the beginning of our discussion today, just have a double check on our schedule. As someone who once did not go to a final exam at PCC as a student and got a 0 speech class, I always like to review our final meeting time and remind folks about what's going on during finals week. Hey, just follow your normal rhythm next week on Tuesday at normal class time, 18th day of March. We will meet for our final exam. You can come on out to Sylvania if you'd like support in person during your working hours on your exam. I'll be here. Or if it's more comfortable for you to be in the world where you are zooming in from, you can be in that world and zoom in, and I will support you during the exam via Zoom. Ideally, in your preparations for the final exam, you will have completed your coursework. So all the homework, all your work on your project, uh, any participation quizzes that just got overlooked or just didn't get quite filled out during the quarter. Ideally, that would all be done by the same day as the final next Tuesday, though of course, due to the vagaries of life and the challenges of getting things done on command, on demand, if you need more time during finals week for any of your work, you can upload stuff through Friday of finals week. Anything at all. Also, if you need time beyond our scheduled 2 hours for the final on Tuesday, we can just figure out what's going to work best for you. On Tuesday, you and I can talk about it during the final. When it becomes clear, you're like, I'm going to need more time and I might have a couple more questions. Just communicate that to me and we'll make sure that your questions won't get lost in a deep inbox or something like that. And they'll get the attention they deserve, which is the right amount to get your questions answered. And so yeah, if you need time beyond the 2 hours of final exam time, just let me know anytime. All right. Oh, and a great question in the chat. Are we going to do quizzes that we missed today? I think that's part of the plan. I think we should do it. Let's start there, actually. We'll start with missed quizzes, and then we'll do a little more final exam, peek in at the topics list in some detail. And then if anything leaps off the topics list as interesting for some review, we'll review that. And if nothing leaps off the list at us, we can go peek at stuff I grabbed between last class and today to share as good practice problems. Okay, that's that. Oh, and then of course, once you're all done with all your work this quarter, we have no class on Thursday next week, so the final exam meeting's our last meeting. And my only ask of you, please, let me put it so you can read this. Hey, that one? What's going on? Why is this not turning colors? Text color. Wait. Oh, there it is. Okay. No, it's not working. What? Do you have to do that? Right. I guess so. After you finished your exam, uh, please, please, please complete my ECC course evaluation. Just any time during finals week. That'll help me get better at my job slowly but surely. And providing specific ideas, specific observations about what worked for you, what worked well, and about what Ralph could improve. All of those things are welcome, and I take your ideas very seriously when I read them. They are anonymous. I don't see the comments until like after the end of the quarter. Like I've turned in the grades and it's been another day has passed. Then I can open them up Wednesday after finals week. Have a cup of tea or coffee, depending on where I'm at, and see what people I worked with this past quarter thought in an anonymous way. So please, please, please do that after you're all done with all your coursework. It will really help me out. All right, now let's shift gears. Let's go check out those quizzes. There's just a couple of us here, but hopefully in the future, if you've been waiting for some quizzes, now's the time. Oh, time out though for me, 1 sec. Okay, now I'm good to go. Let's go to coursework. Good old quizzes. Good old quizzes. Let's see what we've missed in the quiz world. The nearly normal condition quiz. It got skipped. Let's start there. This is going to be, let's just see where it is. It looks like it's after our ANOVA conclusion quiz. We had this nearly normal condition quiz. Let's go see what it says together. Quiz details, boring. Start quiz. Oh, this one. This is a tricky one because we talked about this weeks ago when we were discussing ANOVA hypothesis tests. When checking the nearly normal condition for analysis of a small sample, so fewer than 20 or 20 or fewer observations, which graphical display works best? Histogram, dot plot, box plot, or a normal probability plot, which is what our textbook calls it, also known as a normal quantile plot, which is what GeoGebra calls it. Want to go just look at something together to get our result here? This is long ago. Want a little more support on this one? I don't want to just tell you the result, but I want to show you a picture that might help your eyes see what's what. Let's go say I'm just going to go to good old fashioned GeoGebra.org/classic #spreadsheet. Oops. What if I just typed class. Did that autocomplete me instead of classic, or did I just miss 2 keys on my keyboard? Okay, there's my spreadsheet. In this world of checking this condition, that was when we had those small data sets to work with from our ANOVA calculations supplementary PDF. And we worked through 2 of those from the 3 for the homework, but let's look at the 3rd one for this quiz. I'm going to open up a second. Wait, I'm leaving the quiz for a minute because I want to go get a copy of our PDF. This is a fun, just how this goes. Content, text and technology, slide on down to that ANOVA calculations PDF. Okay. I believe when you did your homework, you worked on exercises 2 and 3 about men's weights and class delivery types. Let's look at this first option here diet plans, just to get a sense of how this works. Look at that. There's three groups there. Their sample sizes are way less than 20. They're all in plan one's column. There's 4 values. Plan 2 and plan 3, only 3 values. So let me steal this. Usually we don't get this much detail in a quiz, but it's just how it goes sometimes. So I'm going to steal this little diet plans graph or problem. I'm going to go back to our quiz. Nearly normal condition quiz. Wait, why am I not in student mode here? What happened to my... When it goes into teacher mode, it's completely useless to navigate and talk with you all about stuff. All those editing options pop up rather than just what we want to work with. Okay, nearly normal conditions quiz. Continue quiz. Took a break there. Okay, there's my quiz. Now, oh, can you tell I'm a little tired? I forgot to grab something we need to do this. We need the class notes to keep track of those data values. Hold on. Sorry. Content. Let's get our course notes, class notes open where we can see them. Great. I'm going to hit all the way to the bottom. It's going to be Wednesday, March 13th, the last day. And it's going to be nearly normal condition. Let's put checking. All right, and there is a small data, 3 groups, small data sets, plan 1, plan 2, and plan 3. I didn't even read the intro. Those are 3 different diet plans to be tested for mean weight loss. Careful, everybody. Diets don't normally work for weight loss. Stick with healthy food and exercise and just don't worry about your weight. Little tip from health professionals there. The entries in the table below are the weight losses for the 3 different plans. For 4 people, 3 people, and 3 people for the 3 groups. Test the hypotheses. There's a lot of work to do there, but we're going to focus in on checking that nearly normal condition. I'm just going to put plan 1, plan 2, and plan 3's. Okay, I'm just going to use plan 1. Let's just focus. Let's check if plan 1 data comes from a nearly normal population. Just focus in on one of them. So I need these 4 values in my spreadsheet: 3, 4.5, 4, and 3. 3, 4.5, 4, and 3. Relax. Okay. Now, I'm just going to hit data analysis for that 1 column of values. And let's look at the options in our quiz. Keep leaving the quiz and going back. Is this the hardest quiz of the whole quarter now because I've had to get all these other things to look at? Because I think it's the most technical one so far. At least for my learning. Okay, I'm gonna make real fast in GeoGebra a histogram of those 4 data values. Okay, there it is. Histogram. I'm gonna grab it, dump it in my class notes. I'm also gonna make a dot plot of those 4 values. Maybe that's too tall of a dot plot. Let's get a dot plot height. There's my dot plot, looking good. Dump it into my notes. Gonna get my window back to readable size. I'm gonna make a box plot. If I go second plot, it's gonna be a box plot. If I make that a little wider. Okay, there we go. I'm gonna make a copy of that. so we can look at these graphs in our notes and decide which one helps us the most. And I'm going to make a normal probability plot, which in GeoGebra, I believe is called a normal quantile plot. We just need one graph for this one, a normal quantile plot, and it's nicely labeled for us. These are nice notes. Better to get the pictures to make the decision, right, than to just try to think about it, especially if we haven't talked about it lately. Okay. Let's look at these one at a time. Does that histogram right there, that particular histogram, help you determine if these data might come from a normal population? We've got two values that are, well, they're both threes, I think. And you've got two other values, one that's at 4 and one that's at 4.5. Yeah, maybe a bit, but maybe. But I'm gonna say it's only 4 values, right? Only 4 values. Likely not enough to show the distribution. Right? You need enough people to go on this diet plan and record their weight loss or weight gain to get a sense of the true spread of the loss or gain that they get under the diet. So of weight loss. I thought it's just whenever a histogram is from a small group, I don't know if these 4 people lost more than people would lose on average, less than people would lose on average, etc. Just not enough detail. Not enough detail. Okay. The dot plot makes it even more obvious. Is that dot plot? I mean, I can see the dot plot like the histogram is skewed to the right, but there's only 4 dots, right? Only 4 dots. Same issue as histogram. No clue, no clue from that dot plot. There's like no hint here. No hint about nearly normal with only 4 values, 4 dots. Box plot. Oh, sweet box plot. You're even worse. The box plot's supposed to know the 5 numbers, show the 5-number summary. We only have 4 numbers. Although the median, you can see it's 3. They do sort out kind of nicely. The median is there at 3.5, and the mean, that the minimum in the first quartile are 3. But again, this doesn't look symmetric. This doesn't look symmetric. Though also you can't, also there's no peak. There's no peak to see. And there's not enough detail. Did you see how I put them the first 3 first? They're kind of all bad for different reasons. No clue here. Okay, sorry, graph. But then this one, this little guy, we haven't seen a normal quantile plot for a while. But remember that the basic idea is if the points are randomly scattered near that line, also near the normal quantile plot line, we can assume a nearly normal population is reasonable. That's how the graph works. That's regardless of how few or how many points you have. Okay, team, what do you think? Are those 4 dots fairly close to that line and randomly scattered around it? Yeah. That's how this looks. That looks. All right, so yes, so this is the best graph. This is the best graph for this condition. This is it, the one for checking this condition. Totally. When you have a very, very small group, you're never going to have enough detail to even see the general trend in a box plot, a dot plot, or a histogram. They'll show you a picture, but it'll often look just kind of like a random mess with just a few dots or just a couple of bars with very low counts. So, but when you get into the normal quantile plot, you get the good picture that can help you determine what you need. And then you know the answer to your quiz is in fact the last one, our buddy, the normal quantile plot. And I'd like to dedicate this quiz to the stats teacher whose first name is Roxy, and I think her last name might be Peck. She's a famous, like, expensive textbook writer, but I once saw a webinar she gave about this topic, and this quiz is basically based on what I learned from her. So you just saw the very short version of a webinar from someone I think is named Dr. Roxy Peck. So good job, Roxy. Cool. That's quiz one. That's first quiz for the day. Good quiz. Hopefully that's our most complicated one. Let's see if they get a little less complicated after this one. Here we go. Back to the quizzes. Don't pause my quiz timer. I don't care. I'm never going to continue the quiz. Just let the timer go forever. Quiz list. Here we go. Ah, linear regression conditions quiz. Let's go. Boring quiz details. Start quiz. Oh, cool. Which conditions must be met before using linear regression to analyze a relationship? We talked about these right at the end of our last discussion. Linearity, nearly normal residuals, which if you only have a few points in your scatter plot, you can check if you've got the values with a normal quantile plot. Constant variability, or so-called homoscedasticity, or all three of those. Yeah, it's all, I'm with you, Lauren R. And if you don't remember, everyone in the world, if you're here today or watching this later on YouTube, when you want to double check the conditions for any of the topics we've worked on all quarter, if you go to our class notes, we do have at the very top of the doc, where's the little slider? Oh, there it is. At the very top of the doc, if you hit up to confidence interval and hypothesis test specifics, that's our giant table. It's right on, it starts on like page 2. And if you cruise on down to whatever topic we're talking about here, it's inference for regression. Well, just even using regression at all, you want to have these same conditions met. And you can see over in this column, there they are. Linearity, nearly normal residuals, constant variation, aka homoscedasticity. Just love saying homoscedasticity. So be sure to select all of the above here for your quiz taken needs, and you will get yet another delightful point for your work. And don't forget where to go look all together for those conditions. They all live in that column for all of our different techniques in that column. And you'll definitely need to check a few conditions for a few different techniques on your final exam. So it's nice to have them together for reference. Bye-bye, little arrows. I know we got another quiz. I could see it below this one when we were going this direction. Let's go check it out. Goodbye, quiz. Goodbye, quiz details. I'm going back to the quiz list. Inference for regression slope quiz. Let's go see what it says. More boring quiz details. Start quiz. if a scatter plot has strong linear, or sorry, if a scatter plot has a strong linear relationship, either positive or negative, between two numerical variables, then a hypothesis test of null hypothesis. There is no relationship between these variables. That is, the slope of the regression line is 0. Will yield a blank p-value, providing blank evidence of a relationship. And it's just high or low, choice for the p-value, and strong or weak, choice for the evidence descriptor. And I know where there's an example to peek at if you want to peek at an example. But see if you can sort those out first. Imagine a scatter plot in your mind that you've seen in our class. A scatter plot showing the relationship between cats' body weights and heart weights. Remember that strong, positive, linear relationship in that graph? Good old cats. Remember those regression tables in those inference chapters? Last column, p-value. And anytime there's a noticeable relationship on the graph, the p-value in the slope row was, hey, we've got a suggestion for low. Let's just check. Let's go peek. I'm going to go right back because just before class, I think what I did was I grabbed the regression table for the cats in case we wanted to talk through regression table stuff. Remember, the second row, let me highlight it. This row tells you details about, first row tells you details about the intercept. Second row, it's labeled with the X variable's name, but it tells you details about the slope. So that's the slope row. And in this p-value column, when you've got a graph that shows a strong relationship, you get a p-value more often than not that rounds off to 0 at whatever level of detail the table shows you. And that's as low as it goes. So low, yes. And then let's go back to our quiz. Whenever, hey, get out of there, you little now useless orange hot dogs. So goodbye to both these high options. Low is good. And when you've got a very low p-value like 0, the null hypothesis is no relationship. The alternative hypothesis is yes, linear relationship. Low p-value, reject that null hypothesis. Low p-value provides strong or weak evidence against the null or for the alternative. Just here at the end of the quarter. Important question. Very low p-value. Does that give you stronger or weaker evidence of the relationship? The same idea 1,000 times this quarter. Saying the same question a million ways makes it always a little interesting to try to ask it again. I'll give you some more details here. No. Slope is 0. No linear relationship. So let me give these to your eyes. Alternatively, slope is not 0. Yes, linear relationship. We got p-value 0. Bam. That is low. Boom. So we have So what? So what do we say about that linear relationship? Oops, not zero. Oh, great question. We got a direct message question. Uh, Office hours are after class at 11 today. And there are also a couple options next week. There's a few options next week. All the normal office hours, I'll turn on my Zoom room. Yeah, yeah. So we have strong evidence. So we have strong evidence against the null, evidence of a linear relationship. Yeah, because that's the alternative. That's the alternative. Great. So low and strong. That is your second option. Great work. Everyone who participated in that little, that little chat and just is listening and hanging out, learning about the hypothesis test. Submit that quiz. Second option, low p-value, strong evidence of the effect, the linear relationship, an alternative hypothesis. Cool. Good job. Okay. Now there's one more quiz there. There's one more quiz. I already saw it on the list. Are you ready? I think it's even got a name you're going to love. You're going to love the name of this quiz. Back to the quiz list. Cruising all the way down to the bottom. Look at that catchy name. Last quiz. Just the last one. Last quiz. Let's go. Last look at the boring quiz details. Start quiz. Well, in stats one, you did a lot of work with data analysis, especially in the first half of that class. And then in stats one, and here in stats two, you've done a ton of work learning about statistical inference techniques, how we calculate confidence intervals to get margins of error on our estimates of population characteristics, and how we can make various kinds of assumptions about large groups, populations, and then see how likely sample data sets look under those assumptions. Hypothesis testing. Options here to describe all that stuff in statistics classes are A, complicated, B, useful, and C, both. Hmm. I think I'm just a little spring forward dumb this week, that hour forward on the clock. Every morning I felt as dumb as a brick for more time than I normally would feel as dumb as a brick. Like my brain's not fully turned on. Well, would it be fair to describe checking that nearly normal condition and getting that, considering those four graphs, is kind of complicated? I hope so. I hope you agree with me. Oh, we've got someone in the chat there with both. So I think complicated is obvious. Every question we've discussed all quarter, even heck, every question about p-values and the strength of evidence, that concept is really difficult for intelligent people to understand and communicate their understanding. Trust me, I've worked with tons of intelligent people learning about it. I know it's complicated. Uh, Also, hopefully at least some of the examples we've seen throughout the quarter have showed you that there are settings where these techniques are useful, whether it's medical settings, psychological research, business and marketing. We've seen environmental impact studies. We've seen questions about, yeah, like marketing stuff. I'm with both. I'm gonna go both. There's two check marks there. I'm with Lauren R. Let's go both. It's definitely both. It can't be not just one or the other. I mean, there might be a rare human being for whom their extremely rare brain doesn't see this stuff as complicated. They'd be very rare. There also might be people who just do not see the utility of this kind of analysis, maybe because it just doesn't make sense to them, or just they prefer a different kind of analysis. But they're also kind of rare in modern days. We're in a culture where data analysis and stats are just used again and again and again in so many ways, both for good and for ill. So there you go. Both complicated and useful. Submit the quiz and you've got all your quiz points. Yay, quizzes. Quizzes are done. So cool. Okay, cool. Clear those drawings out. All right, now let me show you something. Oh, this is great. We've used about a half an hour of class, and we've got a little more time and not a lot of time before the break. So it's a good time to look at the thing I looked at before class and thought, oh, it might be nice to peek at this doc. Let me just show you what I mean. Goodbye, I'm exiting the quiz. Let the timer run for eternity, please. I'm heading into content. See, we've got that little exam prep module down there right above exams, exam prep. There's something good in here for you. See there? Midterm exam topics, we looked at that weeks back, but here's our 244. Final exam topics doc. What I did was I opened up your final exam one day and I described what you're supposed to do on it. So like the very first problem on your exam is going to be about explaining a p-value's meaning in the context of a study, right? Somewhere in the first couple of problems, you're going to have to identify an error type and like what a study's p-value means in context, and if things go wrong, which type of error could it be, and how does that affect the decision making? Things like that. So these are things you've worked on throughout the quarter. Z-test for a difference in proportions. That's going to be on the exam. Goodness of fit testing, guaranteed to be on the exam. Chi-square test, guaranteed to be on the exam. You can see where I'm, yeah. So there's more ideas here of stuff that's guaranteed to be on the exam. When you get into T techniques, you know, I can give you the output for one of our confidence intervals, and you can just focus on writing a conclusion. I can give you the output for various different kinds of stuff and have you focus on the analysis, or I can, give you a choice to make between paired data and independent groups, stuff like that. So there's lots and lots of options here. Good old ANOVA comes back on the exam. You'll see the ANOVA table, and you'll be able to think about the conditions with some graphs and look at a table and think about the p-value and what it means in that setting. Linear regression, just a few options there. Figuring out correlation when you're given R squared, it's not too difficult to figure out the correlation value. Getting the equation for a regression line out of that regression table, figuring out degrees of freedom, stuff like that. And then, hey, look at there. There's the one I picked. I picked the 95% confidence interval for the slope of the regression equation of all those complicated techniques in those last few regression sections. I just picked one thing to do. So you're going to be sure to double check you're confident with that calculation. It does involve that formula. You got to go find the margin of error, and there's a little work to do, just a little bit. And I'm glad to review that after the break if you like. And last question, just what the heck does a p-value mean? And please, please, please put that in your own language and understanding. Whatever makes sense for you, words, pictures, and example, so I can get a sense of where you're at in that developing understanding. And so can you. It's really hard to get that question wrong as long as you communicate what a p-value means to you at the end of two quarters of statistical learning. All right, there's your final exam topics. I blazed past those. I didn't even read most of the bullets, but they're all there for you to gaze upon. And then if any questions arise, like you can gaze upon this during the break, for example, today. And if any of y'all here have any specific questions about any of these techniques, we can check out any of them after the break. And if there's just too much here to choose from in the smorgasbord, I've got a couple of ideas of topics that might be good from this list that we could look at after the break. All right, cool. So let's take a break a little earlier than usual, but I think it's a good time. We'll be back here at 52 minutes past the hour. Yeah, all right, see you soon. Oh, wait, I only put my little back at 9:52 message, because someone had direct messaged me. It went to one of you. Let's get the note to everybody. Back at 9:52, see you soon. I'm back 2 minutes early. That's cool. Hey, if you have perused a little bit that topics doc and you got any specific questions, those would be great. Or if anyone has any other questions, anything they're working on, they want to talk about today, that would be great. Or at 52 minutes past the hour at the end of the break, I've got a couple ideas that we could look at. Yeah, whatever works. Come on, spring forward. Spring forward already. I mean, me. Spring forward, self. Wake up. Hey, great question. And from a direct messenger, totally. I'm going to look that up uh, while we're on break, and then we'll have it to look at right after the break. It's about a question in section 8.1. Oh, I've got a textbook open right here. Line fitting, residuals, and correlation is the section. And is the first problem I asked you to look at, do you mean number 2? This trends in residuals? Is that right? Or is it a different one? Or should I just look? I'm just going to look. Oh, hey, and we're officially back. It's 52 minutes after the hour. Just got a question about what is that first question in section 8.1? Let's go peek at the assignment list because I don't remember which one it is. Section 8.1, I think it's number 2. Yeah, number 2, 8.2. Let's peek at this. And we'll do so over in our old buddies, the class notes. Click, clack. All right. Clickety click. Okay, I'm gonna roll all the way down to the bottom of this thing. 8.1. One more question. Oh, let me make this bigger for me and for you, so we can all see this better. Sorry, that was a little on the small side earlier. Maybe that's too big, though. That's good. Trends in the residuals. Okay, shown below are 2 plots of residuals remaining after fitting a linear model to 2 different sets of data. Describe important features and determine if a linear model would be appropriate for these data and explain your reasoning. Hey, good question. We just took the test. Sorry, we just took the quiz earlier, the quiz asking about the conditions for using linear regression. They really want us to check all 3 conditions, and if any of them are violated, so we could just, if one of them, the 3 is violated, then that would mean that that scatter plots, well, sorry, that residual plots corresponding scatter plot would not be good for regression. So let's get a quick reminder here. I'm going to go to we need to check regression conditions for both scatter plots. So let's start with A. Hey, should I show off my laziness and just go grab the regression conditions list right out of the table at the top of our page here? I'm gonna love my little table of techniques. This is my favorite. I can just go in here and double check I've got the conditions. Any of the regression options will have. They want us to check these 3. They didn't tell us anything about the data sets, so we can't check independent data. but we can definitely check the other three ideas. Back to the bottom where I'm working. Okay. I'm just going to put a little note for that first residual plot. I see a fan shape rather than the desired football or rugby ball, or pick an elliptical shape. So when I look at these, oh, whoops, look at that. So when I look at these conditions, I can go right down. When you see that fan shape, we don't have constant variation. That's homoscedasticity due to that fanning shape. When that's there, linearity, don't worry about this. Don't worry about this. The other two don't really matter. Once you break one, don't worry about this, since three fails. Nearly normal residuals, there's a little trick here. If you don't have constant variation, you might not have nearly normal residuals as well. Though here, who knows, it's linear, but again, don't worry about this since three fails. Like both of the first two could be good, but it wouldn't matter because this is not a good. So we just say here, failing condition three, we shouldn't use linear regression to analyze this relationship. That's the idea. You lose one condition and you're done. Don't mess. For B, well, with your eyeballs, what do you think? Does this graph look linear? This graph right here, does this, give me my orange pen that'll contrast. Does that look like a linear relationship to your eyeballs? When I just drop a pen through that cloud, look like a straight line? Hmm? Don't worry about typing in the chat. Yeah, hey, that's good. Little red X in the participants window. Yeah, that's like a hook shape or a J or an L or something. I don't know. But it's not a straight line. So this flux, I see a curve in the scatter plot, or sorry, residual plot. Uh, Curves like that are usually more obvious on residual plots than they are on scatter plots, depending on like how strong the curve is. Uh, so this relationship failed the linearity condition and should not be used, and we shouldn't use linear regression analysis here as either. Yeah, I didn't put the whole list down. I don't need to worry about nearly normal residuals or constant variation. It's already flunked. The flunking has been done with the curve in the scatter plot. Flunked. These are flunkers in the world of linear regression. Little sad note. Many people in education, in business, in the medical fields even, won't remember to check these three conditions before using linear regression in their analysis. Sorry, plural, in their analyses. That leads to lots of bad. That leads to lots of bad. I'll put it this way, leads to lots of flawed reasoning and often to bad ideas being adopted. At least where I work, I've seen it more than once. People use these kinds of graphs, bad scatter plots, at least bad for linear regression, to argue for doing something that, you know, but the argument's not even being made by the graph because they shouldn't have used it. So, because it's a graph you shouldn't pay attention to. Sad. But it's how things go in life. Great question. I hope that helped with that condition checking confidence using residual plots. All right, team. 10 o'clock strikes. Want to see what I thought about when I looked at the topics list and picked out a couple of practice problems today? Or does anybody else have a question? I feel that springing forward inside my body. It's because at night I'm not tired until it's, later than normal. And then when I wake up, I'm just not, my sleep doesn't work as well. It's jet lag for the whole country. And some of us, some years, it feels worse, like me this year. Oh, great question. A direct messenger is asking, on our final exam topics, when you cruise down near the bottom, we've got this given a linear regression table. First demand is calculate correlation R. Yeah, and the question is, I forget, how do you do that? So let me show you, and I'll even, and these 4 bullets here, getting the correlation together, getting the equation for the regression line, thinking about degrees of freedom, and constructing that 95% confidence interval. Those were going to be the 4 bullets that I would have picked to talk about. So this is good. You have a question that's one of the things I've already planned to discuss. Now let me go grab. And since I already planned it, I already went and grabbed a regression table and dumped it into our notes. It's just above the work we've been doing here. I'm going to grab it. Linear regression review. I'm going to grab it and cut it and dump it down below all the work we've already done. So it's in order of our discussion today. Hey, look, it's our familiar cats regression output. I went and grabbed the cats stuff just because I love cats. So that's the same regression table we looked at in our last discussion about a new topic last Thursday when we talked about margins of error for predictions made with linear regression. We needed this table and a lot of these values to do all that work, though the same table is useful for us for other kinds of questions, like just figuring out correlation. So let's look at these one at a time, just with a reminder. This is a relationship that predicts a cat's heart rate from their body weight. So X values are body weight, Y values are heart weight, and there's the regression table. One thing at a time, calculating correlation R, that's R, and you can see I just copied and pasted the bullets from our final topics right there. I already have them there to help us have a little discussion. This is relaxing. Remember, R is just going to be the square root of R squared. That's it. If you want it to look pretty and mathy, I can do that too. Give me some math. Square root of R squared. Yeah, that's it. Square root of R squared. So R squared is right there. And the only thing we have to be cautious of, it's given by most software in the form of a percentage. For calculations, you always use the decimal version. So I'm going to have square root of 0.6466. If you've got the two options, R squared and R square adjusted, go for the simpler R squared option, as I have done here. That's just a number. Get it from the search engine. It rounds off to 8041 at the same 4-digit, rounding. So cool. Oops, oops, I'm on the wrong doc. Oh, and there's one more note though. Of course, you're always going to get a positive number right here. So this is 8041. That's the square root of R squared. R squared's a percentage or proportion that's positive all the time because of that squaring in its calculation. You just got to double check that the sign of the slope is positive or negative. Don't forget to double check. Slope is positive or negative to get the correct sign for correlation R. Here we can see in the body weight row in the estimate column, that's this number. That's the slope for this relationship. So estimate column, second row is the slope row, labeled with the explanatory variable body weight. That's positive, no problem. So here the correlation is positive 8,041 ten thousandths, or 0.8041, however you like to read it. Here it's positive. So R equals just what we had before. I could even put a plus sign there if I wanted to write a plus sign, but nobody ever does that, so I'm not going to do it. All right. Yeah, finding correlation. Oh yeah, Osei, I see your comment now, only a minute later after you made it. Yeah, if you didn't have R squared and this table, your other option would be to have the whole data set. And then you just dump your entire data set into a spreadsheet, do regression. In GeoGebra, you can hit that show statistics button, and that would give you the correlation R. We saw that with that drug use example in class. But I hope I've made it clear in the final exam topics, I'm not going to give you a big data set to put into a spreadsheet and do regression with. There's just too many ways getting data into GeoGebra can go wrong when people, when their adrenaline is going during an exam. So I try to keep it to as few as possible manipulations of data during our exam. I'd rather give you tables like this and ask analysis questions like these. So yeah, there's that one. Writing the equation for the regression line. Just, it's the reminder, we talked about this a few times last week, but it can't hurt to talk about it again. Regression line looks like y with a hat equals, intercept plus slope times x, right? And notation wise, or in stats notation, that's y with a hat is B0 is the symbol for the intercept plus B1 symbol for the slope times x. I just put a space there because that's how I type multiplication when there's funky typing going on. We just need those two numbers. Intercept B0 is in the intercept row, and the estimate column. Did I get that right? Yeah, intercept is in parentheses. That's the style of this output. Estimate is the column. Here, that's -357 after a decimal. Slope B1 is in the, I'll just call it second row. labeled with explanatory variable name. So that the notes are in general, not just for this particular one. Here it's body weight. And the estimate column, same column. Here, that's going to be 4 and then a decimal 034, 4.034. Just reading it. And then putting it together, we got y with a hat equals intercept -357 plus the slope 4.034 times x. Or if you're like algebra class style, or you could go, just give me a little space here, for y with a hat, if you like it this way, slope 4.034 after a decimal x, and then you can do the subtraction of 357 after a decimal. See that? Order doesn't matter for the BO plus B1x. You can B1x plus BO, MX plus B, whatever style you like works well. And there's your equation for the linear relationship. And if you don't type a hat on y, I don't care at all. I just care that it's got a y and an x, and you're in great shape. All right, cool. Bonus review one here, determine the degrees of freedom. This is pretty relaxing. In regression, degrees of freedom is always going to be, because you have to estimate both slope and intercept. That's 2 parameters. The way that works out in the math is you lose 2 degrees of freedom from your sample size. So regression degrees of freedom, 2 less than the sample size. So here, that's going to be, I've got to go look. Well, sample size doesn't turn up in the table, so it's not in this zone here. But whenever I'm going to ask you this question, you'll be able to look around and find a sample size somewhere. Got 144 cute, fluffy, furry, little characters, little domestic cats, 144 of them. So I'm just going to subtracting 2, that's degrees of freedom. 144 minus 2 is 142. Yeah, no problem. Okay. Want to walk through this confidence interval together too? That's kind of one of the ones I thought would be good for review. This process, we walked through it like once, but that was a while ago, a couple weeks ago. Let's walk through it. Construct a 95% confidence interval for the slope of the regression equation and interpret its meaning. Okay. Let's just remember, confidence interval form is always statistic or point estimate plus or minus margin of error, right? All right, here, our statistic, is slope, B1. We already know the number, 4.034. And our margin of error here, because we're in the world of regression, it's going to be a critical T number, T star, for our confidence level and with the correct degrees of freedom, multiplied by the standard error of the slope, standard error, SE of the slope. We need to calculate critical number T star based on confidence, and we'll do that in just a second. We have standard error of slope B1 in the table, which is nice. Second row of standard error column. Peek up there. Standard error for the slope 250 after a decimal. Cool. Bumps back up to my calculating the critical number chunk of my notes. Remember, critical numbers live in the probability distribution you use for calculations. Here, wait, if you don't remember this stuff, and I don't know why anyone would remember all these details, you can check your notes. We've got our little notes up here. I'm zooming quickly all the way back up to the top. Confidence interval and hypothesis test specifics. Let's see if it can help me out. I want a confidence interval for the slope of a regression line. There we go. T star lives in the student T distribution, and there's a reminder right there, degrees of freedom n minus 2. Okay, and let me show you how that information will help me out. Copy it and bring it downstairs. T star from the student, oh, look at all those weird bonus. Degrees of freedom, n minus 2. We already know that's 142, right? 144 beautiful, soft, little fluffy pod characters. Maybe, actually, some of them are probably pretty big. Got 144 cats. Some of them are going to be big characters. Some are going to be little scrawny meanies, and some are going to be in the middle. Sweet little cats. Some of them won't be sweet either. Some of them will be like little violent monster cat types. Still lovable if you're their person, though. I miss you, Bundre. Now, to get a critical score, I always do, as a nerd, I always go ahead and critical numbers come student T distribution. It's a bell-shaped curve, so I'm going to draw a bell-shaped curve. That doesn't look the most, and that's going to be my DF. That's supposed to be an F. 142. Wow, that's some funky notes. We're talking about a 95% confidence interval. If memory serves, yep, 95% confidence. So that means I need 95% confidence means I need to be able to, cut off all but 5% of the area under my curve in the center. So I artistically draw that. This goes more quickly if I'm sketching on a piece of paper than if I'm using a mouse. But I pretty much, if I'm trying to not make a mistake, I always slow down enough to make a little sketch in this process. It just slows me down to not making mistakes speed. Kind of like driving carefully. And so there's the cutoffs. That area in the center there, that's your 95%, confidence level. The critical number, T star, lives right there at the upper edge of that central 95%. Oh, now I'm even more embarrassed by my bad handwriting. Just switch that to a note that I can read. Degrees of freedom, student T distribution. All right. And then the area that I use to go calculate that T number using GeoGebra or any other good stat software, I can calculate quickly and accurately this area right up here. So that's going to be useful for my calculations. And that little zone, oops, put that over there. The area right here, it's got to be Well, there's 95% in the middle, at least 5% in the two tails. Area in upper tail gotta be the remaining 5% divide 2, which is 0.25, 2.5%. 0.25 after a decimal. That's cool. Oh, and for my notes, make that look a little bit better, like that. And that area right there. Yeah. Okay, with those very clear notes, I can pop over to GeoGebra and quickly calculate that critical number right now, which is what I'm going to do. Oops. Into GeoGebra's world, I head to the probability calculator. I'm using perspectives. It'll just shift me so that it'll fill up my whole screen in a nice way. Hey, look, my little drawing's in a good place on the screen to help me out rather than make it harder to do my work. So I don't have to move it around, which is nice. I got my notes here. Degrees of freedom 142, student T. There's my options. Student is the second option. If it's been a while for you messing with these degrees of freedom, 142, just bump that up. Look at that. Remember, as degrees of freedom get higher and higher and higher, the T distribution gets closer and closer to a normal curve. If you're nerdy, when you type in your degrees of freedom, you just look up at the standard deviation. The higher your degrees of freedom gets, the closer this gets to 1. So at this point, there's just slightly more area out there in the tails of the student distribution than there would be in a normal distribution. Though, here I just go clickety-clack, looking for that right tail area to be 2.5%. I just put that percentage right there in the percentage zone. Hit go, and my critical T-score is 1.9768. Cool. That is great. And then for my notes, because I'm sharing these with all of our crew, I'm just going to put a picture of this entire screen with my little drawing that helped me go. Wait, artistically, I'm not satisfied. I'm going to move my drawing to be up here because I did the drawing first, and it'll look better. Graphic design is my passion. Website name, calculation, picture from GeoGebra, it's all there and good. You can see that the critical T-score is the hardest part, or the most complicated part of this calculation, because it's the number we actually have to go find ourselves in this setting. There we go. Now it's in our notes. Cool. All right, and now, can I get that whole thing on my page? Yes, I can. So we're gonna have our slope is 4.034. We're gonna add and subtract the critical number 1.9768. Yep. Times the standard error, which I typed up somewhere. It is 0.250, 25%. Or sorry, these aren't percentages, 25 hundredths. And that's my calculation. I can go get the boundaries. Lower boundary. I take this one, get rid of the addition symbol. Upper boundary, get rid of the subtraction symbol. Yeah, I'm going to go get those numbers calculated using the nearest calculator. Which is the search engine of this computer. Lower boundary is about 3.54, 3 54 hundredths to the nearest hundredth. Oops. Seems fair. Or well, wait. Oh no. Oh, no, that's good. That's good. Okay. And then the upper boundary is this number here. Copy that calculation, dump it in the nearest calculator I've got, my search engine. That's 4.53 or 4 and 53 hundredths, rounded to the nearest hundredth. So confidence interval 3.54 up to 4.5. Shoot. Okay, that's the calculation result. We got it for slope. Bang, done. Got it. Love it, like it, kind of complicated. The reminder here being that if you have to do this critical number calculation, there's a little work to do. And it does involve getting into the correct distribution, making sure you're looking for the correct zone and find that value. Double check with me during the final if you're on this path and you need to like a reminder or to double check on your work. So you don't make a random mistake when you're under a ticking clock with your adrenaline going. Okay, and then there's one last step here. We did all this work, do all these calculations, interpret the meaning. Okay. Meaning depends on meaning of slope, right? That's going to be our x here is at body weight in kilograms. I remember that unit from last week. Y here is cat heart rate, grams. Okay. Slope. Remember, this is from last week. I drew lots of stars and hearts by this in the notes every time it came up. Let me see if I can state this in a relaxed way. Slope predicts change in y for a 1 unit increase in x. Right? That's in general. So generally. So here, I'd put it this way. For each additional kilogram, so see that? For 1 more kilogram, I'll make it even more that clear. For 1 more kilogram of cat body weight. So I'm focusing on my 1 unit increase in x. This model predicts between, confidence interval range, 3 and 54 hundredths of a gram and 4, oh, sorry. Oh, no, that's right. And 4 and 53 hundredths of a gram greater cat heart rate on average, or in the on average, if you want. And then don't forget with 95% confidence in the prediction. Ooh. Yeah. Again, it's like describing the meaning of these confidence intervals is almost always every bit as challenging as getting the calculations done in the first place. So, but there you go. There's my example. One more example of a complicated description being necessary to unwind what we're talking about. In the world of the slope, it's always complicated because it's got this relationship between what you'd predict as the change in the response variable for a 1 unit increase in the explanatory. Tricky to say and type out. So again, during the exam, if you're working on a problem like this one, and at some point you will be, if I'm there, like if you're still working and I'm still in the room and we're all working together, and you want to double check that you're writing that up clearly, feel free to ask me and I'll help you out just by double checking your work and letting you know, oh wait, that's not actually quite how that works. I could give you a tip to clean things up. All right. Linear regression exam preview. It was cuter than the exam's going to be because there were cats. So that's good. Or is that bad? I don't know. Wait, can I do uh wait, I'm in, how do I get an emoji? I want an emoji. I want a cat emoji. Do I type like emojis? There we go. Cat. Uh there you go. Cat hearts, right? Good emojis to wrap up the example. Okay. All right. Any other questions brought to mind while we're working, or do you want me to go to my one of my bonus examples I grabbed earlier? But while you're thinking, if you're trying to think of something, think. I'm going to go look at some examples I grabbed earlier. We'll see if one of them jumps out at all of our eyeballs of those of us here. So again, between last class and this class, this morning, I went and grabbed a few examples just out of the text, but see here they are, a few review exercises, for the final, just that'll end up in the table of contents. I picked a hypothesis test where they give us a hypothesis test to do, comparing miles per gallon for some cars that are automatic or manual. I also picked, that's a hypothesis test example. I also picked a confidence interval example that uses the same data and context. I thought it might be nice for review to sort of look at those kinds of calculations two ways. I picked a bonus hypothesis test review, and there's a note here, ignore part C on this one. It's a level too complicated for our final, something that's not on our topics list. Not on our topics list, not C. C simply isn't on. C simply isn't on final exam. It's not among the topics that are good. But you can see here, it's a depressing problem about prison isolation experiments. Gives us some data, gives us an ANOVA table. There's an ANOVA table. Parts A and B are great. What are the hypotheses and what is the conclusion of the test with 5% significance level? Those are great questions because you can sort out what the ANOVA hypotheses are and use the complicated table to get your conclusion correct. You're doing pretty well for having met ANOVA just a couple weeks ago in your life. So what do you think? Do you like cars driving around, automatic and manual? Or do you like for some hypothesis testing or confidence intervaling? Or do you like a little quick peek at how the ANOVA table works again and how the ANOVA setup works? What do you say? Or do I choose? If I choose, I've already got an idea what I would choose. So you just say your choice or say you choose and we'll go for it. Maybe ANOVA? ANOVA is the quicker one too. So let's do ANOVA And even with 15 minutes left, we might have time for ANOVA and for the other one that I would select, which is I'd probably go for the hypothesis test review as well. But they're both hypothesis tests, so that's good. Let's do ANOVA first because it's quick, and then we'll peek back at this fuel efficiency one as well. I'll just do this ANOVA one right where it stands in the world here. It's a depressing setting here. A prison isolation experiment. What a weird way to write solitary confinement, which is a torturous way to punish people for crimes. Another exercise introduced an experiment conducted with the goal of identifying a treatment that reduces subjects' psychopathic deviant T-scores. Those are scores that test how someone responds to like being bossed around, I think, on a psychological like test thing. The score measures a person's need for control or their rebellion against control. In the other exercise, people evaluated the success of each treatment individually. An alternative analysis involves comparing the success of treatments. The relevant ANOVA output is given below. Now, I don't have the 3 treatments listed here. There's 3 of them. One of them was, oh goodness. There's 3 treatments. One of which is meant as like a placebo, where people just, after being submitted to solitary confinement, they just kind of watch a video of like some dogs or something. One was to watch a video that offered some like relaxation techniques tips. That was like the second treatment. And maybe the third group, just nothing, like no dog video, no video with relaxation suggestions, just you got out of solitary confinement and now you're sitting by yourself taking a test to see about your need for control or your need to rebel against control. Yeah. So hypotheses wise, let's just go through in the world of ANOVA, hypotheses, basic hypotheses structure is always kind of the same. It's just null hypothesis assumes all groups means are the same. Alternative hypothesis is that they're not all alike. That is, at least one mean differs from the other. You can view the language either way. So here, wait, let's do this like this. Here we'd have null, all 3 treatment groups mean it's like a change in their score on that test, or their mean, I'll just say mean scores. I think it's, yeah, their mean scores are alike or the same. And alternatively, let me do this, treatment groups, just for language. All 3 treatment groups mean scores are alike. They're the 3 groups. Alternatively, mean scores vary, right? You can say it in lots of different ways, just that they're not alike. They vary, or are not all alike, aren't all alike. At least one's different. There might be a couple that are the same, but at least one is different from the others. Enough to pick up in the test. All right. Then part B, what is the conclusion of the test using a 5% significance level? Just remember, to make a hypothesis test conclusion, you got to find the p-value. P-value is in the PR rater F. That's the notation for the probability of getting an F statistic bigger than the F statistic calculated in this ANOVA table. Short for, that's the long way to say the p-value. And so the notation's different. That's it's P equals O 461. And then we just got a 5% significance level, right? We've got 0461 is less than, sorry, 5%. P is low, null must go. And then what that means in context, the conclusion needs to say something about these groups' test scores, test score averages. Researchers have evidence that the mean scores for these three treatment groups are not all alike. Bam. Now, part C, we would need to refer back to like a different, we would need the means and the standard deviations of all the different groups, and there's more complications in there that we wouldn't want to worry about for the pairwise testing to compare things. And we're not going to worry about that for fine parts. So C, reminder, don't worry about this. Don't worry about this. Don't worry about it. If you ever are in a research setting where someone does want to do those pairwise comparisons, you will be working with someone who has enough statistical understanding to hopefully do them wisely. There's an adjusted significance level to do that helps make those make sense. Cool. That just took a few minutes. Does that help people just big ANOVA basics, hypotheses, location of p-values, just right there in that table, labeled. They could have just put a p-value at the top of the column. Again, make me the dictator of statistics, and I will change the way things are labeled. And I'll keep changing them until everybody on Earth in stats introductory classes can understand what the heck we're talking about and connect their understanding to what's written down in the book. Someday, stats will be less impenetrable if we all fight for it. You can see my rebellion against control score is high. Although my need for control score might also be high. I want to be the dictator of statistics. I'm kidding. I don't want to be the dictator of statistics. It's always a lie. I never want to be the dictator of anything. Okay. We got 7 minutes. Do you want to peek at this other hypothesis test one? I just yanked it out of the book. This was the one I would peek at if I was going to peek at one of them. Want to just peek at it, getting it set up and thought about it a little bit? However many details we can talk about in 7 minutes. Let's do it. Fuel efficiency of manual and automatic cars, part 1. Each year, the U.S. Environmental Protection Agency, the EPA, releases fuel economy data on cars manufactured in that year. At least up until this year. Who knows what they're ever going to do in the future, or if the agency will even exist in a matter of months, since our federal government's trying to destroy all of the regulations that protect us from things like pollution. Holy good night, what a nightmare. Pardon me. Below are summary statistics on fuel efficiency in miles per gallon. So this is US data, obviously, with the US units. For random samples of cars with manual and automatic transmissions. That's interesting. So some of those cars could be like SUVs that have low mileage, and some of them could be like Corollas or Accords, or even a Prius that has, really good mileage, but they do use gas. Assume that conditions for inference are satisfied, meaning no car's fuel efficiency directly impacts any others. So independent data, both within each group and of course between the two groups. Cool. Along with it being safe to assume that for these samples that are not at least size 30, they're drawn from nearly normal populations. That's not hard to believe based on those fairly symmetric box plots. The picture is good for checking that. Okay, there we go. Do these data provide strong evidence of a difference between fuel efficiency for these two types of cars? Let's sort this out. Provide strong evidence. We're at the end of 2/4 of statistics. That always means do a hypothesis test, right? So don't just look at the numbers and look at the graphs and say, yeah, that's great evidence. And, and use the p-value to analyze the situation. That's what it means in stats class. They're never, well, hey, friend, give me why? Computer, what are you? Sorry, computer's being mean to me. I'm trying to draw a dot and it won't do it for me. Okay, so let's do that. Hypothesis testing, there's 4 steps, right? These are listed out in their basics at the very top of this doc, but I know them by heart from many years of this work. Write out your hypotheses, double check the conditions for inference are met, calculate that p-value, and you get a test statistic along with it that sometimes your stats teacher might ask you for on an exam. And, use the p-value to make a conclusion. Okay. 3 minutes. Oh, gosh, I just want to. Hypotheses are the most important thing. You cannot succeed without them. Oops. So let's get those straight before class ends, and then we'll probably just jump to the calculations. The question here says, do these data provide strong evidence of a difference between average fuel efficiency of cars with manual and automatic transmissions in terms of the average city mileage? It's a huge mouthful. The old guideline for writing hypotheses is, if the effect you're curious about is truly happening, so if there is a difference, that's the alternative hypothesis. Yes, something's up. So I'm going to say for my alternative, city MPG differs for automatic and manual cars. Yeah. And I'm going to say average, right? Mean or average city miles per gallon differs for both. Null hypothesis would be nothing's going on. That would mean there's no difference, right? No difference in mean city mile per gallon. Oops, gallon. Heck, cutting and pasting is going to help me out here for automatic and manual cars. And notice I'm talking about the entire populations here that from which we drew those random samples. Cool. Okay. See what we've got here? For calculations, oh, we have 1 minute. The most crucial thing on your final exam is using the correct thing. What kind of hypothesis test are we doing here? No difference in mean city miles per gallon is the null. Alternatively, it's that there's a difference for these two groups. Two groups. Difference. Difference of means. Difference of means. Difference of means? Believe it? Difference of means. Remember that topic? Like that little moment right there. What kind of hypothesis test am I going to have to do once I've got everything set up? That little moment is the one that on the exam can be challenging because you're looking back over 10 weeks. of working with all sorts of different kinds of hypothesis testing. So while you're working this coming Tuesday, if you have any questions about that as you're working, those are great questions for your teacher. And I will, elicit from you your knowledge and understanding till we can find the way to get you to the correct thing. In GeoGebra, that's called a t-test difference, uh, difference of means, right? So in GeoGebra. And we are out of time. So if you want to practice that t-test for the difference of means and practice your conclusion and double check you know those conditions between now and the exam, that might be wise. That could be a good thing to do. And if you want any other tips or pointers as to where to look for, all of you'll notice what I did for exercises to review. I just went and grabbed even stuff out of our textbook that looked interesting to me. If you're not quite sure which things look good for exam review, you can compare to the topics list. So if you're looking at something in the book and thinking, should I practice this? Check if it checks out with these topics. And if it does, yeah, practice. And if it doesn't, maybe skip it. Oh, great question in the chat before we go. What time are office hours next week? I think they're at the normal times. Let's just double check my schedule. I might have eliminated one of them just because most of my exams happen early in the week. But next week, you can see, oh, they're all on the calendar because my last exam is Thursday afternoon. So early Monday, so like 9:30 to 10:30, right after our class time. So that would be 11 o'clock on Tuesday, or after our ghost class on Thursday, 11 to noon. Or heck, if someone wanted to make an appointment, you could contact me during class time on Thursday. If someone's wrapping up their work and want to talk about some questions, there's time on Thursday during class time. But there they are, 9:30 to 10:30 Monday and Wednesday, 11 a.m. to noon, Tuesday and Thursday. And there's other times in the week. You can see Wednesday afternoon, I'm free to make appointments. Thursday early, free for appointments. Friday, we can make appointments. So lots of appointment options as well. Gaze at that calendar, direct messenger. Imagine what time works best for you, and you can just let me know via email if you like, or just as we're getting finished here, I can put it on my calendar if you want an appointment. All right. All that being said, great last question, and just one more reminder. Thank you so much for your hard work this quarter. We had some weather struggles. I had some health struggles in February that kind of put me behind on feedback. Thank you for your patience with that. I've been struggling all quarter. Your class ended up being kind of middle of feedback being bad, not as slow as the one in which it's the slowest and not as quick as the one where it was quickest. But you all showed me patience and understanding there, which I appreciate. So yeah, if you have questions between now and Tuesday, the ideal thing to do would be to, on Monday, come talk to me at 9:30 a.m. if that works with your schedule, or contact me about a Monday afternoon appointment. You can see I'm free starting at 1-ish. I'm giving another final that day, so I might not be right in my office at 1. But if you want to come talk to me, in that afternoon, I don't have to leave campus until about 4:30. So we can figure that out. All right. Great work. Farewell. Have a good one. And thank you, and thank you, and thank you, and you're welcome, and you're welcome, and you're welcome. Awesome. Farewell.